so I'm going to ask you guys to test out your metal. Draw at least one resonance structure, because there are a number of different options. Draw one resonance structure for the sulfate polyatomic ion, and do so, find that one resonance structure at least that's going to have a minimized formal charge. Alright, so we are going to come back together, draw this one last structure for the day, our one last Lewis structure for chapter 6, and then we're going to wrap it up with a nice bow. That's not to say that obviously we're not going to continue drawing structures, but we have learned all of the rules necessary to draw both the base level and the exceptional level of Lewis structures. All right, so we're going to follow our rules for drawing sulfate before we can establish whether or not we can break them. Right, we can't just jump into drawing an expanded octet. We're going to get a base level foundational structure by following the rules first. So our sulfate is going to have a total of 6 valence electrons from the sulfur, plus 4 times 6 electrons from each of these oxygens, plus an additional 2 from the -2 charge. So we're going to have 2 extra electrons in the structure, giving us the -2 charge. The total number of valence electrons, therefore, is going to be equal to 32 valence electrons. So we're going to take each of these 32 electrons away from the atom, or the atoms in the molecule, and then we will start redistributing them as we need to. Now, between the sulfur and the 4 oxygens, each of these atoms has the exact same bonding capacity. So how do we know which one's going to go into the center? Well, between each of these atoms, sulfur is kind of the odd man out. So even just conceptually, if we're paying attention to things like symmetry and aesthetics, it would make sense for the sulfur to be in the middle and our 4 oxygens to be around it. Another way to kind of critically evaluate and determine that the sulfur is going to be in the middle is that sulfur has an element or an elemental number that is greater than or equal to number 13, which means that it has the potential to expand its octet. This rule of thumb doesn't always mean that you will have to expand your octet, but it's kind of something nice to look out for. If you have an element that is greater than number 13 in some type of structure, it may end up being in the center in order to accommodate an expanded octet. All right, so for all of these reasons, we place sulfur in the middle, oxygens outside. We have currently placed 2, 4, 6, 8 electrons in the structure, giving us a total of 24 electrons left. So we're going to take those 24, place them around the terminal atoms first. We're still going to follow that rule. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So all 24 of the electrons have now been placed around our oxygens in the terminal positions. No electrons left in the pool. Because we have no electrons left in the pool, this is going to be the point where we can kind of look at and establish are all of the valence counts, or all of the octets satisfied. And after that, as now kind of a new additional critical evaluation, we're going to calculate formal charges. All right, so our oxygens each have 2, 4, 6, 8 electrons around them. Sulfur also has 2, 4, 6, 8 electrons around it. This means that all of the octets are satisfied. Oh, and of course, because we have a -2 charge here, we're going to add a -2 charge in brackets around it. Before we call this good, though, we're going to have to, again, establish what are the formal charges. If this structure has minimized formal charge, then, perfect, we're done. We can just wash our hands of the problem. We have the most stable Lewis structure. If it is not the most stable Lewis structure, though, we're going to have to start pushing electrons around and expanding an octet, right? We're going to have to break the octet rule to make something even more stable. So let's start with our oxygens. Each of these oxygens looks the exact same. They all have the same kind of characteristic bonding pattern. Let's see, so I'll do this one. Each of these oxygens has 6 valence electrons. We're going to subtract out our 1, 2, 3, 4, 5, 6 total lone pair electrons. We're going to add that to 1/2 of the bonding pair, which is 2 electrons present. This gives us a -1 formal charge, and that's going to be true for each of these oxygens around the structure. Now we can already kind of see that we are going to end up in a situation just like the chlorate ion before, where the valence shells are all completely filled. We have nice complete octets, but it looks like all of the formal charges are kind of pushed away from the minimum. We don't have the ideal electron distribution across the entire molecule. All right, our sulfur, just to be explicitly clear, is going to have a formal charge of 6 minus no lone pairs plus 1/2 of 8, 2, 4, 6, 8 in all of the bonding pairs, giving us a total of +2. Yeah, this sulfur definitely does not have a minimized formal charge, so we're going to have to start pushing some electrons around. In fact, the total formal charge of the sulfur in the center tells us how many lone pairs from surrounding oxygens we should push. In order to give sulfur the amount of electron density it needs to reach a formal charge of 0, we're going to need a total of 2 more pairs of electrons to come in towards it in the form of bonding pairs. So here's where the aspect of resonance comes in. We have 2 electron pairs necessary to push towards sulfur, and we have 4 different options from where we can grab these electrons. So I'm just going to pick this pair up on top, push this one in towards the center, and I'll pick this one. Because why not? Again, we could have picked from the oxygens on the left or right. We could have picked like top and to the right, like any of these combinations would do, just so long as we have 2 additional bonds, 2 double bonds present in towards this sulfur. Because we've pushed 2 additional bonds in towards the sulfur, there's now a total of 2, 4, 6, 8, 10, 12 electrons bonded to it, right? 12 electron pairs in the form of bonding. This means that now as we adjust the count for our formal charge, 6 valence electrons, still no lone pairs, but 12 total bonding pairs gives us a total formal charge equal to 0. And the oxygens that we've taken the electrons and pushed them in towards the center, we get a different electron or a different formal charge count for them, since there are 6 valence electrons minus 4 lone pairs plus 1/2 of 4 gives us a grand total of 0. So now we have a sulfur that is completely satisfied. We have 2 oxygens, this one as well, that are completely satisfied. And we have 2 oxygens also left over with that -1 formal charge. Sadly, these are going to have to be left as is. Again, since we're working with a polyatomic ion, the total count, the sum of all of the formal charges inside of the molecule, must equal the charge of the molecule on the whole. So we have a -1 formal charge on one of our oxygens, a -1 formal charge on the other oxygen, the sum of this is -2, and there is a total of a -2 charge present in the sulfate anion. So this structure that we have drawn, in fact, I'll just write a cleaner version over here, is the most stable Lewis structure that we can draw for sulfate, at least in one of its resonance forms, and we can conclude this because we have minimized the formal charge. We had to expand sulfur's octet to do it, but again, because it's greater than element number 13 on the periodic table, it has access to those high energy empty d orbitals where it can just slip all of the electron density into that back pocket. We don't have to worry about the expanded octet. The electrons have places to go. We're not explicitly paying attention to what that new electron configuration is in general chemistry, but suffice to say that the electrons are stable where they're going. They have a place.